Okay, I welcome you all to the discussions of carbon-13 NMR spectroscopy. This is the video that is produced as part of the efforts to flip the classroom in the chemistry and biochemistry department of UMass Dartmouth. We have had extensive discussions about proton NMR spectroscopy. So today we are going to look into the NMR of carbon. If you notice, it is carbon-13. It's not carbon-12 NMR. Why is that so? We'll talk about that in briefly. Also, the carbon-13 NMR seems to be deceivingly simple. Some people must be thinking that it's cool compared to proton NMR spectroscopy, where you have to worry about the spin splitting, multiplets, and all sorts of things, right? So, though it looks simple, but it's not as simple as it looks. To collect the data, it takes more time, more efforts, more sample. So that's one of the reasons why carbon-13 NMR spectroscopy was developed by scientists much later than proton NMR spectroscopy was developed. Okay. To compare both of the information that we get, proton and C13 NMR spectroscopy, both of them give us the information about the number of chemically non-equivalent nuclei. Either it's hydrogen or carbon. In carbon NMR we get carbon information, in hydrogen NMR we get hydrogen information, right? Information about the hydrogens. And we can also deduce some information as to what is it attached to, what is the hosting atoms, hybridization state, or what is attached to the carbon, or what is attached to the respective nuclei. Okay. So we'll compare as we go along. We would make comparisons between proton and C13 NMR spectroscopy. Whatever you learned in hydrogen NMR or proton NMR should be transferable to carbon NMR as well. So you should not quite be worried if I just compare some things to proton NMR, because we have had extensive discussions about proton NMR. Some of the things would be compared to the proton NMR spectroscopy as we proceed in our discussions today. Having said that, some of you must be wondering, why not carbon-12, right? Carbon-12 does not have unpaired spin. So for a nuclei to be observed in NMR spectroscopy, or to have the NMR effect, a nuclei should have magnetic momentum, which is caused by the unpaired spins of the nucleons. If the nucleons have the spin, so should be nucleus. I am not sure whether nucleus will also spin, but a nucleus cannot have spin unless nucleons have unpaired spin. Carbon-12 has even number of protons and even number of neutrons, so the net spin is cancelled by those even number nucleons. So carbon-12 nucleus does not have unpaired spin. Is one of the reasons why carbon-12. It is the reason why the carbon-12 cannot be observed in NMR spectroscopy. Or, to put it other way, carbon-12 is of no use for this particular spectroscopic tool, because it doesn't have a magnetic momentum. As we learn in proton NMR spectroscopy, only those atoms which have odd number of protons will have spin. Those atoms with an odd number of neutrons will have a spin. Atoms with an odd number of both protons and neutrons will have a spin, but atoms with an even number of both protons and neutrons will not have spin, and they are magnetically inactive. They don't have magnetic field of their own, so we cannot perturb the spin states, so we cannot observe them in external magnetic field, that is NMR instrument. So it's one of the reasons why this particular tool is not applicable to all the nuclei. Okay, only certain nuclei can be observed in NMR spectroscope. So today we are going to talk about C13 NMR spectroscopy. So if an atom or a nuclei doesn't have spin, it would not generate a magnetic field. In order to generate a magnetic field, we talked about in terms of physics, it should have a spin of its own. The spinning electrons, as you can see here, the current which goes in the loop would produce a magnetic field. Or the other way around, a magnetic field which is inserted between a coil would also produce electric field. So vice versa can be produced. An electric field can produce a magnetic field, a magnetic field can produce an electric field, and it's perpendicular to the direction where things are moving here. If this, for example, if the nucleon has a spin along this axis, the magnetic momentum that it generates would be perpendicular to the axis of spin. If it were to spin in this direction, then this magnetic field would be in perpendicular to that direction. It would be aligning with the external magnetic field. This is the direction where the external magnetic field is and then facing the NMR. So the spinning nuclei can align with the external magnetic field, or it can oppose the external magnetic field depending upon the spin state. Okay, so that's the fundamental principle of NMR spectroscopy that we learned already. So carbon-12 does not have any of these properties, so it is not magnetically active. It is only carbon-13 that is active. So it is insensitive compared to proton NMR. For example, if you have 100 carbons in a molecule, only one of them would be magnetically active. Only one of them would be carbon-13. So the signal that is generated for carbons is not from carbon-12, it is from carbon-13. And as we know, the abundance of carbon-13 is only about 1.1%. So you need more sample to have carbons, enough carbons to produce the signal that you want to see, because it's C13 that produces and it's low in abundance, and the reason why you need more sample, more time, more sophisticated instrumentation to get the C13 NMR spectroscopy. In advanced classes we do teach more other factors that cause this kind of discrepancy between C13 NMR and proton NMR, but at your level it's just enough to learn that the abundance, low abundance, is one of the reasons why the C13 is only about 5,000 times less sensitive than hydrogen NMR is. Okay. The other factor that is causing to this kind of insensitivity is the gyromagnetic ratio or magnetic gyric ratio. The gyromagnetic ratio of C13 is only about 1/4 of that of hydrogen. So it's 4 times insensitive compared to hydrogen. Okay, less sensitive compared to hydrogen. In other words, hydrogen is a bigger magnet, so it would produce a bigger magnetic field compared to carbon-13 nuclei. Proton would be a bigger magnet. Okay, so the magnetic field that is generated by the nuclei is very less here. How does it transfer to the intensity of the peaks? We learned in one of our discussions that the energy difference that is caused by the external magnetic field between alpha spin state and beta spin state is proportional to this proportional to gyromagnetic ratio, right? And the external magnetic field. Here the equation is given. The delta E is the difference between the alpha spin state and beta spin state. The difference in the energy states of alpha spin state and beta spin state is given by this equation. As you can see, there are two terms that are featuring in this equation in the numerator: gyromagnetic ratio as well as external magnetic field. Depending upon these two, there would be proportionate difference between the alpha and beta spin states. And if you have a radio frequency that would match this energy difference between the two spin states, the spins would flip to a higher or to a spin state where it's opposing the external magnetic field. If this is the direction of the external magnetic field, this particular nuclei is opposing the external magnetic field, and this is in alignment with the external magnetic field. That's the reason why it's at lower energy and this is at higher energy. And we keep the magnetic field constant, and we use a varying frequency of the radio waves, and then we try to match this energy difference. And when the energy difference is matched, it produces a peak. Right? We measure the emittance or absorbance, and that would produce the peaks on the NMR. So the bigger the difference, the better, the stronger the peak. It would be bigger when you have higher magnetic and gyromagnetic ratio and higher magnetic field. But for carbon-13, the gyromagnetic ratio or magnetogyric ratio is small compared to proton. That's all so far we discussed. Hope you understood. Two things that we discussed, that is abundance of carbon-13 is low. The gyromagnetic ratio of carbon-13 is low compared to proton, and carbon-12 is magnetically inactive. Okay. I'm going to skip some of these we already discussed, and this is how the energy difference between the two spin states is proportional to the magnetic field that we apply. The external magnetic field is increasing in this direction, the energy difference is increasing in this axis. Okay, and this is the radio frequency. So if you keep the magnetic field constant, and then the frequency would be different depending upon the gyromagnetic ratios of different nuclei. So how does it affect carbon-13 NMR spectrum collection? Let's say you have a magnet of 4.73 Tesla, and if you were to observe hydrogens in that magnetic field, and the spin states of hydrogens or protons would split so much that it would require this wavelength to cause this precession or spin splitting, or to cause a resonance. Spin flipping. Okay, so a 4.73 Tesla would induce only about the difference that could be matched by the radio frequency that has 50 megahertz. The same magnetic power would induce a higher energy difference in case of hydrogen nuclei between the two spin states, and for carbon it would be smaller level. So the magnetic field goes down. The strength of the external magnetic field has to be increased. If you want to induce any meaningful difference between the alpha and beta spin states, you need to increase the magnetic power, the external magnetic field. Okay, so to observe carbon-13, you need a powerful magnetic field. Okay, why is that so? The delta is also proportional to the delta E is proportional to the number of nuclei in this state, the beta spin state. The more the nuclei that we can flip, the stronger the signal, right? Okay. Do you have any questions so far? If not, we would proceed further. And just to recollect all things that we learned, we have radio frequency light, that's oscillator, and we have external magnetic field. We place our sample in the probe that we talked about already, how to collect, how to make the sample, what solvents to be used, and how the instrumentation works. It's pretty much same as how the proton NMR works. It's the same magnet, same NMR instrument that we use, same NMR tubes, just that we dissolve more compound because we need to have more carbon-13s to give us NMRs, okay, NMR signals. So let's say we have a constant magnetic field, and we place our sample that has very concentrated solution of our compound into the probe, and then we pulse it. There's something called, we supply the radio frequency. There are some mathematical programs, that computational programs, that we can automatically set the experiments, and they would collect the data in the form of FID. A lot of data points are collected, a lot of frequencies are overlapping here. This is time domain frequency. So this is converted into frequency domain by a process called Fourier transformation, and you would observe carbon-13 signals. And as I said, if you have 100 milligram sample, after a couple of scans, a couple of minutes, if you stop the instrument, stop the experiment and do the Fourier transformation process, you would get a spectrum like this, where the peaks are not as clean as you saw in hydrogen NMR. They are submerged in very noisy area, right? This is called noise. These are signal. The signal to noise ratio is very high here. So in order to get a smooth baseline, you need to have thousands of scans and you need to have more sample. For example, a proton NMR can be collected in a milligram sample, but for C13 at least you need 20 to 30 milligrams for a decent C13 spectrum, okay, in decent amount of time. So if you let it go for longer time, the signal to noise ratio improves and you get better signals and the noise ratio goes down, and that's again due to the low abundance of carbon-13 and less gyromagnetic ratio of carbon-13. Okay. If you understood these two terms and if you can compare the process of collection of data to that of HNMR, we are set to go forward and start looking at some of the C13s and try to analyze them. Some of the features of C13 NMR are listed here. Each signal in C13 NMR corresponds to a unique type of carbon, same as in proton. Chemically equivalent hydrogens give one signal, right? All the chemically equivalent hydrogens would produce only one signal, one peak. Chemically non-equivalent hydrogens would produce more peaks. The same is true here. If you have more chemically non-equivalent carbons, you expect more peaks in the carbon NMR. If you have less number of chemically equivalent carbons, you see less number of peaks. And the intensity of each peak is not directly related to the number of types of carbon. So there is no such thing called integration in carbon NMR. You can probably integrate, but that's of no use because it's not reliable information. There is a reason for that. We'll talk about that. The chemical shifts are usually reported as a difference from that of the reference TMS in ppm, not in the hertz. We invoked something called delta value chemical shifts. We reference it to TMS, so wherever you measure, the delta value doesn't change. Whatever the machine you measure, either 200 or 300, because you are taking the difference from that of your reference, that is TMS sample, and you are dividing the difference with the instrumentation frequency in the hertz, so it gives you a unitless scale that's called ppm scale. So the chemical shifts pretty much like proton NMR, just that instead of 1 to 10 we have here 0 to 10, we have here 0 to 200. Okay. So how do we analyze carbon-13 NMR? Same as how we did in proton NMR. In proton NMR case, we looked at the number of peaks, chemical shifts, integrations, and spin splitting patterns to deduce the information out of given proton NMR. We can do the same thing here, but however there is no integration and no spin splitting in carbon-13. We have to worry about only two things: number of peaks, chemical shifts. That's much more easier. So some of the students like carbon-13 NMR compared to proton NMR. Probably if you are given with both the NMRs and asked to assign the structure, you should look at the carbon-13 first, just to see as to what type of carbons, what type of connections does it have. Okay, so this is the carbon-13 NMR of simple compound called acetic acid. How many different types of carbons do we have here? 1, 2. So there are two chemically non-equivalent carbons, so they are magnetically non-equivalent, and as a result we get two peaks. One is towards the shielded area, one is towards the deshielding area, one is towards downfield, the other one is towards upfield. Again, this downfield and upfield could be confusing. This has some historical relevance because in olden days they used to keep the frequency constant, the radio frequency, the electromagnetic radiation used to be constant. The field was varied, and as a result that technique we have this paradoxically conflicting terms. Though this is at lower ppm, we call this as upfield, though it's higher ppm, we call that as low field. So if you don't want to get confused, you can remember this as towards low chemical shift or towards high chemical shift. That kind of takes care of that conflict. This is called downfield, this area is called upfield. This is the low chemical shift values, low delta values, and this is higher delta values. This is where all the shielded nuclei would come, this is where all the deshielded nuclei would come, towards your left hand side of the spectrum. If you are facing the spectrum and 0 is towards your right hand side, that right hand side is shielded area, the left hand side is deshielded area of the molecule. So we have 2 peaks here that corresponds to 2 carbons. When you are in carbon NMR, just focus on carbons mostly. We'll have some other type of spectra, we'll talk about that. But when you are analyzing the single line spectrum, you focus on the number of types of carbon. You can safely ignore the hydrogens. And when you are in hydrogen NMR, focus on hydrogens. You can ignore the carbons, so to speak. They don't couple with the hydrogen. Okay. So you have to learn that to shift your focus to the nuclei that you are observing. Okay. Don't count hydrogens as separate chemically non-equivalent nuclei, and that should not be deceiving you. You don't find a signal for hydrogens, though it's magnetically active, because we decouple the hydrogens. We'll talk about that in a minute. We adjust these frequencies such that we only observe carbon NMR. It's like your radio station. There are hundreds of stations that are available, but depending upon how you tune your transition set, you'll selectively hear some of the stations that you like. And the same is true here. And we selectively pick the experiment that we can only observe carbon or hydrogens. That's called decoupling. We'll talk about that. So, depending upon the first parameter, the first concept of the NMR, C13 NMR, is to learn how to analyze the peaks by counting the number. The number of peaks in a given NMR is proportional to the number of chemically non-equivalent nuclei. If you have more chemically non-equivalent nuclei, you get more peaks, right? Are equivalent to the non-equivalent carbon 13s, carbons. Okay. So, for example, all these compounds here, cyclopropane, cyclobutane, cyclopentane, cyclohexane, have one type of chemically non-equivalent carbons. So you get only one peak. This CH2 is same as this CH2, this CH2 is same as this CH2, and so is that, so is that. So you have symmetry, and symmetry simplifies the NMRs, right? One would argue that this can exist in board form and chair form, and the chair itself can flip into 2 different chairs, but all that happens so fast that we cannot observe them differently in carbon or spectroscopy. Probably if you have substituted cyclohexane, and if it were to be locked in one form of the chair, then that would give different number of peaks than the other form of the chair. For example, equatorial tertiary butyl cyclohexane, if it is locked in the equatorial fashion, it would have a different type of NMR than axial tertiary butyl cyclohexane, right? So the symmetry simplifies the number of peaks. Though this is made up of 3 carbons, this is made up of 4 carbons, 5 carbons, 6 carbons, you get only 1 peak. So it's kind of difficult to assign the structure of a compound if you have 1 peak, and that's all, they're all coming around 20, and so it could be any of this. That's why you cannot just assign the structure of the compound based upon one piece of information. It's like forensic science. You have to collect your clues from many places and then sit down with all the data that you have and nail the culprit. Same is true with this structural analysis. You collect some information from carbon NMR, some information from proton NMR spectroscopy, and some information from mass spectroscopy, functional group information from IR spectroscopy, and then deduce the molecular formula and then write the possible structures and see which one accounts for all of them. Okay. So to summarize this slide, you should be able to relate the number of peaks to the chemically non-equivalent carbons. So let's take some more complicated structures here. This is dimethylbenzene. It has an element of symmetry along this axis, as you can see here. And that or plane of reflection, whatever you want to call. Probably learned that in inorganic chemistry. So that simplifies the number of carbons. So this carbon is same as that carbon is same as that carbon, and then I'm pointing with the mouse. This carbon is same as that, and this same as this one. So this part of the molecule is a mirror image of this part of the molecule. So they would have less number of peaks. They would overlap. For example, this methyl carbon would overlap with that. So they would have same chemical shift. If they have same chemical shift, you get only one peak. Okay, is that clear? So if you have more number of symmetry elements, you get further lower number of peaks. For example, this alkene has two-fold symmetry, and as a result, this methyl is same as this methyl, and this methyl is same as that, so you would only observe one methyl, though this molecule has four methyl groups. Same is true, this carbon is same as this carbon, so you get one peak for this carbon and one peak for this carbon. Essentially, you have only two lines or two peaks on the carbon NMR. This would have four lines. As blue would give one peak, the red would give one peak, the pink one would give a peak, and the black one would give a peak, and the rest of them would be overlapping. Right? They're not colored in the actual molecule, just to kind of explain. These are colored here, but all the carbons are unique, right? Anyhow, so symmetry simplifies the spectra. That's the fundamental take-home point here. If you have symmetry in your molecule, you can expect less number of peaks. If you don't have symmetry, you get more number of peaks. Symmetry simplifies the spectra. Good, right? It's helping you. Symmetry helps students. Anyhow, this is quinone, and as you can see, you have plane of symmetry in this axis, whatever you want to count it as, and it has probably two-fold symmetry, and as a result, you get only 1/4 of the number of carbons that you have. So you cannot just say it has only 4 carbons, though it has 16 carbons. So the 4 carbons are this carbon, that, and this carbonyl peak. So you have 4 carbons in the carbon NMR for this molecule. The moment you disturb the symmetry by placing a substituent, for example, this is hydroxylated quinone, only one hydroxy is substituting at this alpha position of this compound, and as a result, you would get a peak for each of these carbons because there is no symmetry. I cannot cut this molecule into 2 equal halves. So as a result, each carbon is distinctly different than the other one chemically and magnetically, and as a result, you observe more peaks in the carbon NMR. So the symmetry simplifies the number of peaks, or symmetry simplifies the spectrum. So you can probably sit down and count the number of carbons that each one of these would give in a given carbon NMR spectrum. Okay. For example, this is bromobenzene, and this is orthocarbon is same as this one. This is metacarbon, the same as this one, and then the paracarbon. So 1, 2, 3, 4 peaks would be observed for this molecule. This is diethyl ether. This methyl group is this methylene group is same as this methylene. This methyl is same as that methyl. So you would only observe half of the molecule. In other words, you get only 2 peaks. This would give 3 peaks. This would give how many? 3 peaks. Because this carbon is different. This carbon is different than this carbon, but this carbon is same as that carbon is same as that carbon, so you get only 3 peaks. So try to find out if a molecule has symmetry or not. If it doesn't have symmetry, you have to look for the number of carbons that a molecule has. You got to essentially observe all those carbons. There is pretty rarely overlap in carbon NMR because it's spread out from 0 to 200. As opposed to the proton NMR spectroscopy, which is only from 0 to 10, and there is a lot of splitting pattern to the proton NMR spectroscopy or proton signals, so they overlap at times. But however, carbon-13 is much more informative in the sense you can observe all the chemically non-equivalent nuclei separately. They are spread out, and there is rarely overlap if their chemical shifts are not same. Their chemical shifts are same when they are chemically equivalent. Okay. So for example here, this is diethylbenzene, para-diethylbenzene. So this has a symmetry and as a result you get only the peaks for the half of the molecule. I guess this methyl is same as that methyl, this methylene is same as that methylene, this carbon is same as that carbon, so 3 total so far. This is same as that, and this is same as that, this is in turn same as that one, so you get 4 peaks for this molecule. Okay, the moment you take off the symmetry you get more peaks. This has about 9 carbons, you get 9 peaks for this. There is one overlap here as you can see, but that also can be zoomed. When you zoom it, you can find out there are 2 peaks in it. So distinctly different peaks are obtained for chemically non-equivalent carbons. But remember, these signals are originated from carbon 13, not from carbon 12, and as a result you need to have more carbon. I think that should help you to analyze the number of peaks or to predict the number of peaks for all these compounds. This has a lot of symmetry elements, so you would get less number of peaks, whereas this compound also has symmetry, so you got to learn how to identify symmetry. This doesn't have symmetry, you can expect more number of peaks. If you have any questions about this, I would be happy to help you. So try and solve this slide on your own and then see me if you have any questions. How many peaks do you expect for this? 2, right? All these methyls are unique, and so they are not unique, they are one and the same, and this carbon is different than this carbon, so you get 2 peaks, one for methyl, one for this quaternary carbon. Okay, I'm going to skip some of the slides. So but you have to be careful when you have situations like chiral centers, rings, so you better draw out the structures in a 3-dimensional form and then assign the number of peaks. Otherwise you could be doomed and there could be some traps, right? For example, this compound has 2 methyl groups on this carbon, but you can have a free rotation. That rotation would make these 2 methyls equal to one another. In other words, this methyl is same as this methyl chemically and magnetically. There is no reagent that you can differentiate this methyl from this methyl. There is no reaction. So as a result, they are chemically equivalent. If they are chemically equivalent, that Pople notation tells us that they are magnetically equivalent as well. These 2 methyls are called enantiotopic methyls. The enantiotopic methyls would have the same chemical shift. So as a result, the number of peaks that you can expect for this compound is much less, at least less by one number, because there is symmetry at least in this part of the molecule. Whereas when you have diastereotopic carbons, for example, because of this chiral center, even though you can have free rotation here, this methyl is trans to this hydroxy, whereas this methyl is, let's say if you were to write it absolute configuration like using alpha and beta bonds, one of them would be cis and one of them would be trans, and as a result they would have different chemical shifts, different chemical properties and different magnetic properties. So you would expect 2 peaks for these 2 methyls. Okay, that's shown here, right? Okay. If you have any questions, again feel free to stop by. This is like same as diastereotopic hydrogens that we discussed in the class. As long as you have simple rotation, and if you don't have chiral centers, alkenes, rings, you are safe. Once you have these elements, you have to be more careful to assign a given NMR spectrum. Okay, so there are some examples again here for your benefit. Try and solve them and find out the number of carbons that you would expect. Try to simulate the spectra and then compare. There are some programs. ChemDraw, for example, has a tool that can predict the C30 NMR. Quite accurate. So sometimes it's as we expect, right? If you do the NMR experimentation, if you obtain the carbon NMR, it would be same as the one that is predicted, because there are so many computational tools these days, so many data points, and you can load all those things and develop a software that would assign NMRs for unknown structures. Okay, so anyhow, so try and solve this slide and find out the number of signals in proton decoupled C13 NMR spectrum. We will talk about what is called proton decoupled C13 NMR. So let's compare the two tools that we have been learning once again here. So the C13 signals are spread over much wider range than hydrogen signals, making it easier to identify and count individual nuclei, individual chemically non-equivalent nuclei. The following slides will show the proton NMR and C13 NMR spectrum of a molecule called chloropentane. It's much easier to identify the compound as chloropentane by carbon-13 NMR than proton NMR. Let me just show you how simple it is in case of carbon NMR. This is the proton NMR. Proton NMR does give some valuable information that carbon NMR doesn't give, but carbon NMR also is valuable, that it tells us some information very quickly than the proton NMR. For example, we have four peaks here. 1, 2, 3, 4, 5 chemically non-equivalent nuclei, but some of them are overlapping here. See, this is because of the two methylenes that you see here. So that's not the problem in case of carbon NMR. Then you have to see the integration here, right? You have to see the spin splitting pattern, integration, so on and so forth. Whereas in carbon NMR, you just count the number of signals. You have 5 carbons and you have 5 carbons. This is from the solvent CdCl3. Deuterium has some coupling to carbon-13, and that's why the carbon CdCl3 comes as a triplet in C13, and it doesn't show up in proton NMR, but it comes as chloroform in proton NMR. H is seen in proton NMR, but D is seen in carbon-13. The deuterium frequency is much closer to the carbon frequency, I guess. So the deuterium residual peaks can be seen in carbon-13 NMR. So there will be some solvent peaks like DMSO D6 will give a peak, acetone D6 will give a peak, CdCl3 will give some peaks. So you got to be careful to ignore the solvents. Don't count these as number of carbons. Normally it's around 77.7. So if you see a triplet kind of a peak on there, that's from CdCl3. So, and there might be some TMS at times, so you have to ignore that as well. Sometimes TMS is so low in its quantity, the entire sample, so you don't see a strong peak that we normally see in proton NMR for TMS. But nevertheless, instrument references that, and it can be fixed according to the TMS peak. So this is the C13 NMR of chloropentane, and as a result you can easily identify this as a chloropentane by counting the number of carbons. Pentane 5, so there are 5 and there is no symmetry, so there are 5 carbons. So it's much easier to analyze the structure of a compound. At least the number of carbons can be easily reduced from the carbon NMR because it's not overcrowded, it's spread over 200 ppm, and rarely there is overlap in carbon NMR. A separate distinct peak appears for each of the 5 carbons. Okay. So however, if you go back and you look at the intensities, though they are all for 1 carbon each, the CH3 is giving a carbon, and this CH2 is giving 1 peak, and this other 2 CH2s are giving some peaks, and this is giving a peak, but their intensity is not same because it's not like hydrogen anymore. There is some relaxation delay. You remember we get the peaks because of their relaxations. When they relax back to the alpha spin state, they emit the energy, and we record that. If all the nuclei are not relaxing at the same rate, there is discrepancy in their peaks, right? That's one of the reasons why the integration is not very useful in carbon NMR. For example, the methylenes give more intense peak than methyls, than tertiary carbons, than quaternary carbons. In other words, secondary carbons give stronger peaks than primary carbons, which are much stronger than tertiary carbons, which are much stronger than quaternary carbons. This decrease in intensity is because of the discrepancy or inequality in the relaxation times. Okay? If you allow time between the pulses, let all the nuclei relax, then probably it can be integrated. There is a special experiment for that. It's called gated decoupling or gated C13. So at your level, it's very advanced. Just know that the integration doesn't make sense in a simple decoupled carbon NMR. Okay? Especially the quaternary carbons are pretty small. See, this is a quaternary carbon of this carbonyl. We'll talk about why the chemical shifts are at different places. But at this point, what we are trying to learn is the shape and the number of peaks. The shape, we just learned the number of, how to analyze the number of peaks. We are now looking into the shapes of the peaks. They're all singlets, so nothing to worry about the spreading pattern. But the size of the peaks, the intensity of the peaks is different for different types of carbons. The methyls and methylenes are normally in this range, and alkenes and alkynes are somewhere around 100 to 120. The aromatic carbons are in this range. The carbonyl compounds are in this range, from 160 to 200 or so. So normally the quaternary carbons would come at a higher field. At a lower field, downfield compared to methyls and methylenes. This is downfield, this is upfield, and this is shielded, and this is de-shielded, right? Okay. So this is a summary of our discussion so far. The proton NMR integration reveals the relative number of hydrogens per signal. In other words, the area under the peak is proportional to the number of hydrogen nuclei. Okay. The C13 NMR integration is kind of quite not as reliable. So you got to be careful in doing that. Okay, it's rarely useful due to the slow relaxation time for carbon 13s, especially those carbons which are not attached to protons would relax slowly, and as a result they give smaller peaks. For example, in this case we said quaternary carbons gives less intense peaks compared to methylenes and methyls, which are much taller. Okay, so the integration would make no sense here. Each peak is representing a chemically non-equivalent carbon. Okay, so this molecule has 1, 2, 3, 4, 5, 6, 7, 8 different types of carbons. So you can expect 8 peaks. I'm ignoring this. This is from CDCl3, and I'm ignoring this peak that is from TMS. And then you can count 1, 2, 3, 4, 5, 6, 7, and if you zoom this area, you can find that there are 2 peaks. Though it looks like as though they are overlapping, you can zoom out and then you can see that there are 2 peaks. So we have total 8 peaks here. So each chemically non-equivalent carbon would give a peak, just the intensity is different depending upon whether they're quaternary, tertiary, or primary, secondary. Okay. So anyhow, I'm going to skip these slides. Now, having learned about the type and the shape of the peaks, we will shift our attention to the chemical shifts. Chemical shifts are affected usually by the electronegativity of the groups that are attached to the carbons under consideration. Same as proton NMR spectroscopy. If you have a carbon that is in turn attached to electronegative atom, those hydrogens that are attached to that particular carbon would have a different chemical shift. Right? The same is true here. The electronegativity of different groups attached to different carbons would give different chemical shifts. The hybridization states also matter. Alkanes come at pretty high field, upfield, and then the alkenes, then the alkynes, then the alkenes, and then the aromatics, and then the carbonyls. We already saw the discrepancy between the alkynes and alkene hydrogens in proton NMR. The same explanation holds good even for the carbon NMR. Okay, the anisotropy, magnetic anisotropy, right? So anyhow, so this is my readout for remembering the chemical shifts roughly. It's not precise, but at least you know the ballpark area where to look for. If you have alkanes made up of sp3 carbon, you would look between 0 and 40 or 50. If you have electron withdrawing groups attached to alkanes, you would look between 40 to 70. If you have alkyne carbons, you would look at between 60 to 80. If you have alkene carbons, from 80 to 120 or 130, depending upon the type of alkene. Is it attached to electro deficient or is it attached to electropositive element? Okay, electron donating groups. The aromatic carbons would vary depending upon the density, electron density of the sextet. If you have electron withdrawing groups on the aromatic ring, you have downfield shifts this side. If you have electron donating groups, you would have the carbons coming in this area. Carbonyl carbon, this is very important window of C13. If you have carbonyl compounds, you can expect the peaks anywhere from 160 to 220, and depending upon the type of carbonyl, you have different areas. This is just rough classification of the functional groups, right, and their appearance on the carbon 30. Then you have to go specifically into carbonyl compounds and then see what type of carbonyl compound is it. So several functionalities that appear directly on C13 NMR which are not visible in proton NMR. For example, you cannot see quaternary centers in hydrogen NMR because they don't have hydrogens, so there is no way you can see a quaternary carbon in a hydrogen NMR because the hydrogens are responsible for there, right? So we tend to overlook the quaternary carbons pretty often when you analyze the proton NMR. So that's the reason why you should first take a peek at C13 NMR and then go for the proton NMR analysis. The ipso carbons, again, those are the carbons which are attached to different groups like bromides, alcohols, aromatic bromides, aromatic alcohols tend to be ignored in proton NMR, but they can be seen in C13 NMR. The carbonyl carbons, again, they don't have hydrogen, so they don't appear, except for the aldehyde. Aldehyde has one hydrogen attached to the carbonyl carbon, so you can see that peak, and the carboxylic acid has a hydrogen attached to oxygen, so probably you can identify those two functional groups, but rest of the carbonyl compounds cannot be analyzed using proton NMR. So the carbon 13 NMR is much more useful in that sense that the functionalities that cannot be seen in hydrogen NMR can be seen in C13 NMR. So if you were to tabulate all the discussions that we had so far, this would be something that I would arrive at. This is much more divided scale of chemical shifts, or the handout, much more finer analysis. If you have different carbons, saturated carbons, all of them are sp3 carbons. Depending upon the number of alkyl groups that are attached to, the chemical shifts are different. The general ballpark area for alkanes is 0 to 55 ppm. If you have primary alkanes that has only methyl and then only one alkyl group, they would come around 4 to 20 or 30. Secondary carbons, which are in turn have two alkyl groups, you would expect them to vary from 12 to 50. For each substituent, even if it is carbon, you get downfield shift. Okay, you get higher chemical shift. Okay. For olefinic carbons also it's true. The tetrasubstituted alkenes would come at a higher chemical shift than the monosubstituted or disubstituted alkenes. This is the carbon that we are considering. That see, the bold carbon is what is this chemical shifts correspond to, not for the rest of them. So this is the carbon under consideration that would come under so on and so forth. Allenes again have different types of chemical shifts. There are different types of carbons in allenes. These terminal carbons have a different chemical shift than the center carbon, because though this is sp, looks like this is sp2 hybridized, but it is not. What is the hybridization of this carbon? That's sp hybridized, and that sp hybridized one is should be somewhere around 80 or so, but I'm not quite sure as to why this allene carbon comes so downfield. Probably I'll have to look up that, but take it from me that it's very downfield one. The acetylenic one, which have a triple bond here, those carbons come normally 60 to 90. The benzenoid ones, the carbonyl ones, as I mentioned, the carbonyl window is very important. Depending upon the chemical shift, you can assign whether it's an aldehyde or a ketone, or whether it's an ester or an amide, or some carboxylic acids. Okay, so the chemical shifts is very characteristic for carbonyl compounds, carbonyl groups, carbonyl carbons. It's like IR spectroscopy. In IR spectroscopy, you can tell amides and esters apart. You can by looking at the frequency, right? Looking at the peaks. Same is true here in the carbon NMR. The nitriles and the nitrile triple bonded carbon, this is C triple bond N, would come at around 120. then diazomethanes, if it's attached to nitrogen, then it would come around 145. So try to memorize this, try to at least remember them roughly, and then I would give you a handout in the exams and then the recitation, so you would be able to do the problems. Again, I'm going to skip this slide because it's the same thing again and again, different way of putting things. So if you were to see the trends, the pi bonds cause downfield shift, electronegative atoms cause downfield shift, the carbonyls cause downfield shift because of the anisotropic effect and sp2 hybridization and the electronegative effect. All of these are cumulative here. Oxygen is more electronegative than carbon, and there is a pi bond, and there is sp2 hybridization, so on and so forth, right? So this is again the same way that we've been discussing, just that the functional groups have been listed here. So this would be handy for you. So if you zoom the carbonyl range, if you want to go further into refining the carbonyls, you have to zoom from 110 to 220. That part of the NMR can be printed separately, and then you look at the position of the peaks, and then depending upon the position, you could analyze it as a nitrile or an anhydride or acid chloride, amides, esters, carboxylic acids, aldehydes, conjugated ketones, and ketones in that order. Ketones are the farther downfield. So if I have the same molecular formula, and if I get 1 degree of unsaturation from that given molecular formula, and if there is oxygen in that molecular formula, if I am uncertain whether it's a carbonyl or an aldehyde, just look at the chemical shifts. If it is at 220, it would be a ketone. If it is at 200, it would be probably an aldehyde. Okay, that's the benefit of carbonyl shifts of carbon-13 NMR spectroscopy. So there are some examples given here. This is 2-methyl pentane, and that spectrum is given here. It has 6 distinctly different carbons, 5 distinctly different carbon, because this methyl is same as that methyl, and these two are chemically equivalent. So you get 1, 2, 3, 4, 5 peaks, and you can see there are 5 peaks. So you can go on to count like that, and this peak, now we having learned the chemical shifts, we should be able to assign that peak to this carbon because it's attached to electronegative atom compared to rest of them. And what would be this next downfield peak here? This would be something that is having more substitutions. This would be this CH2 or this CH2 or this CH2 or this methyl, right? Because this effect can transfer to some extent to this methyl and to this methylene, but this being methylene, it has 2 alkyl substituents, and so this is down. So that would be the methylene, and so forth. Like that, you have to try to look at the local environments and try to assign the chemical shifts. And this is an NMR for bromopentane, 3-bromopentane. And as you know, there is symmetry, so the number of peaks are kind of less. 1, 2, 3. And this is probably simulated NMR rather than what is taken NMR instrument. So that's why you don't see the CDCl3 peak. Otherwise you would use the CDCl3 peak, or it's pretty concentrated sample where the solvent is so less compared to the sample, so you don't see the CDCl3 signals, so to speak. And the alkenes, you have 4 peaks in the alkyl region, 2 peaks in the alkene region, and again which one is more downfield? Is this the carbon that is corresponding to this, or is this the one? That again depends upon the substitution pattern. This is doubly substituted, so this is much more downfield than this one. Okay, so not only now we can count the peaks, not only we can understand their shapes, but we can also assign respective carbons depending upon the substitution pattern. The aromatics, and this is an electron-rich aromatic ring, so the more or less the peaks are in this area, and we do have an alkene, so all of them are kind of coming in this region. And there are some ipsocarbons, this carbon and this carbon and this carbon, they are quaternary carbons, so the quaternary carbons are less intense compared to the rest of the carbons. There is a carboxylic acid here. This carboxylic acid has a carbonyl. If we are unsure about it, just draw the functional group out completely. C double bond O, OH, and then you see that C double bond O is coming at 180, and that's the reason why you can assign this as a carboxylic acid. And it has the rest of the baggage, and that baggage is seen here, right? And this is an ester. As you can see, this carbonyl peak is now little upfield, about 170-ish. So that's an ester. Moreover, the number of this also has a methylene, that's 60, because this is attached to oxygen. So the chemical shift of this is at much higher than the chemical shift of rest of the carbons. Okay, so that's how you analyze different spectra. This is an amide. We are looking into carbonyls especially here. This is an amide carbonyl, and this amide carbonyl has a chemical shift about same as an ester, but the fact that it has a nitrogen, so you can say that these are amides. They are a little upfield than esters, because nitrogen is not as electronegative as oxygen. And also it has 4 carbons in the side chain, so it has 4 carbons here. And there is no symmetry here. So we don't see the nitrogen in carbon NMR, so we don't have a peak for nitrogen. If you want to see the nitrogen, you have to take nitrogen NMR. That's N15 or N14 maybe. Anyhow, the ketones are much downfielded, de-shielded, right? Because of substitutions as well as sp2 carbon and the electronegativity of the carbon, compared to that of aldehydes. For example, you see this around 200-ish, but whereas carbonyl has 220. Ketone carbonyl has chemical shift of 220, whereas aldehyde carbonyl has a chemical shift of 200. Okay. So you can distinctly tell them apart, that either they are aldehydes or ketones, depending upon the position of the carbonyl. And this is the C13 spectrum of geraniol. Geraniol is a terpene, and it has alkenes, and those alkenes are seen here. The aliphatic carbons are seen in this direction, this way, in this part of the spectrum, and you can list them, you can tabulate them, and you can count the number of carbons. Okay. And we can distinctly assign them. Of course, this alone will not tell us, there are other ways of assigning them, but nevertheless, by looking at the chemical shifts and the atoms that are attached to, for example, this carbon is attached to oxygen, so that is this carbon, and this carbon is attached to alkene, so that's probably a little downfield. Okay, so by looking at the structural features, hybridizations, the atoms attached to the carbon, one can derive the chemical shifts. One can analyze the chemical shifts of a given carbon NMR. How about spins? We learned the types of peaks, shapes of the peaks. We learned that integration doesn't have any sense in carbon NMR because of the discrepancies in the relaxation times. We also learned about the chemical shifts. Now to move the last parameter that we learned, that is spin-spin splitting. Is there spin-spin splitting in carbon NMR? Theoretically, it should be possible to see the carbon-13 coupling, but the probability of seeing that is very less. It's somewhere in the noise that we saw in the carbon NMR, right? Because what is the probability of having a carbon adjacent to the carbon-13 adjacent to another carbon-13? Unless you have enriched your sample by starting off with the carbon-13 nuclei. Those are called isotopic labeling synthesis, but we don't do that kind of a synthesis. We just normally take the natural abundant carbon compounds that are derived from petroleum sources. So the natural abundance is 1.1. So that the probability of having that situation where one C13 is adjacent to another C13 to couple with each other is much remote than what we have seen in hydrogen NMR. So though theoretically one should expect it, practically we don't see that. However, we do see proton carbon-13 coupling because hydrogens are quite abundant, and each carbon-13 would have hydrogen. Hydrogen is magnet, carbon-13 is also magnet, and they couple with each other. They influence each other's magnetic field. They influence the effective magnetic field. B0 is that we saw, right? B0 is an applied magnetic field. B effective is the effective magnetic field that a nuclei experiences. This effective magnetic field is influenced by the local magnetic fields, and the local magnets are hydrogens on C13. You don't find another C13, but so that's why we don't see the C13 coupling, but we see C13 proton coupling. So we don't need to consider C13 coupling unless you are doing enrichment studies, isotopic labeling studies. Okay. However, we do see the coupling of C13 and protons because the hydrogen abundance is quite high. However, we can do away with this coupling. If you want to have the coupling, you can have. If you don't want to have the coupling, you can turn it off. There is something in the instrumentation part which is called a decoupler. You turn the decoupler on, it nullifies the effect of hydrogens. That's more to do with experimentation. It's a little advanced at your level, but just to know just to explain theoretically, I have some slides here. So either you can collect a coupled spectrum or decoupled spectrum. Okay, we are referring to hydrogen, right? We don't have C13 coupling. So when we say decoupling spectrum, it is proton decoupled carbon NMR or proton coupled carbon NMR, hydrogen coupled carbon-13 NMR or hydrogen decoupled carbon-13 NMR. Okay, and the coupling constants are pretty high. They are in the range of 100 to 200. In proton NMR, we learned that coupling constants are anywhere from 0 to 20 or 30 hertz at the maximum, right? Or maybe not that much even. But here in the carbon-13, you have higher chemical shifts because of the heteronuclear coupling. It's not homonuclear coupling. Hydrogen is a different type of magnet and carbon-13 is a different type of magnet. Hydrogen is a bigger magnet, C13 is a smaller magnet, so there is, because of the gyromagnetic ratios that we talked about. Okay, so there is coupling. So if you want to understand what we were talking about, the C13 coupling, we only have one C13 molecule out of 100 molecules, so there is no way that this C13 nuclei would find another C13 nuclei to couple with each other. So it's very pretty remote chances. One probably 10,000 or so would have that coupling, and that would go into the noise. Okay, so I'm going to skip some of these things that we already discussed, these points. So now, how about the other way around? Did we see C13 coupling in the proton coupling? In the proton NMR? It does couple. If the hydrogen can influence C13, C13 should also influence hydrogen, but we never talked about C13 hydrogen coupling in proton NMR because it's very insignificant. In other words, if there are 100 hydrogens, only one of them would be on carbon, that is C13. So out of then the 99 carbons would not couple with the hydrogen, only one carbon is coupling. So that would be very small amount of peaks and they would go into the noise. As you can see, this is a molecule where you have 99% of carbon-12, only 1% of carbon-13, that's a natural abundance. So there's only one hydrogen that is attached to this carbon compared to the 99 hydrogens. The 99 hydrogens produce these peaks, that one hydrogen that is in turn attached to, or the hydrogen that is in turn attached to this carbon would produce the peaks that would have spin splitting, but those splittings would be gone into the baseline, the noise, so you don't see them. Okay, so just to kind of clarify if you have the doubts. So how about the other way around? All the carbon-13s would have magnets attached to them because if they are not quaternary ones, let's say if they have primary C13, secondary C13, primary, tertiary C13, then they would have different types of, different number of hydrogens. For example, this CS3, if it were to be C13 carbon, it has 3 magnets attached to it. So n+1 rule should give us a quartet. This carbon should be a quartet. And this would be a triplet because it has 2 magnets attached to it, right? And so how many should this be? This doesn't have any magnetically active nuclei, so it gives a singlet. And this has 3 magnets attached to it, so this would give a quartet. Because of these 3 local magnetic fields, the probability of arranging these 3 magnets is 4 possible ways, right? So because of that we get quartet for that particular carbon, and that is this quartet. This quartet is much high field. Upfield, right? Sorry, this one, that's TMS. Okay, so the proton coupled NMR is of some information. We can now find out from the coupling pattern as to whether a given carbon is secondary or a primary or a quaternary or a tertiary, right? Quaternary doesn't split. So if something is singlet in a carbon 13 NMR that is coupled with proton, you can say that that's a quaternary carbon. Right? So the types of carbons can be deduced by coupled NMR. But however, this is only useful in a simple molecule like this. If you have a complex molecule, we already talked about this. If you have a complex molecule like this, codeine, I think it's quinine kind of compound, the peaks are overlapping here because of the splitting. Each carbon is now further split because of the hydrogens, and there are too many hydrogens and too many carbons, so it kind of overwhelms. It becomes detrimental instead of helping us, right, to analyze the different types of carbons. So the proton coupled NMR are quite useless here. It gets pretty busy pretty quickly. So is there any way we can do away with this coupling? That's what is called decoupling. So what we do is we nullify the effects of hydrogen nuclei by irradiating with a frequency that essentially converts all the spin states to 0. So in a sense we silence this nuclei. It doesn't have any effect on this nuclei because we turn the decoupler on. If the decoupler is on, it decouples the effects of the hydrogen on the C13. That's the instrumentation part. If you are more interested, I can show you how we do it in our brand new NMR that we just got from Bruker. Okay, it was funded by NSF, right? Anyhow, so a proton decoupling would help us to analyze the NMR pretty quickly because now everything is singlets. Because we took the hydrogens out of the scene, the effects have been nullified, so the hydrogens do not talk to the carbons, and carbons are themselves coming at where they should be because there is no local magnetic field that is disturbing them. So now the signals, the chemical shifts are proportional to the external magnetic field. The effective magnetic field, in other words, is same as is decided by the hybridization and the electronegativity of the atoms, right? Okay, so the sample is irradiated with 2 different radio frequencies such that the hydrogen effects are nullified, one to excite all the C13 nuclei, and second to cause all the protons in the molecule to undergo rapid transitions, and the spin states have been brought to 0, right? On the time scale of C13 NMR spectrum, each proton is in an average and effectively constant nuclear spin state. With that, the result of proton C13 spin-spin interactions has been taken care of. That's been decoupled. So to compare the broadband decoupled spectrum with that of coupled spectrum, this is called off resonance spectrum. It's coupled spectrum. The proton is coupling to carbon. Okay, and as a result, carbon singlets are multiplets here. If you take off the effect of the carbon, effect of the hydrogens on this carbon would be a singlet. So should be this carbon, because it doesn't matter now how many hydrogens are attached to each type of carbon. Okay. So for example, even the primary is a singlet, even the secondary is a singlet, and the quaternary is also a singlet. So This is called decoupled spectrum. This is called coupled spectrum. The decoupled carbon NMR is quite useful, especially in the case of complex molecules. You get another example here. This is off resonance spectrum. That is a coupled spectrum. This is broadband decoupled spectrum. The broadband. So this is simulated one. And again, you don't see CDCl3 here. I don't like this kind of spectrum, or maybe this is a CDCl3. Anyhow, so it has 4 or 5 carbons. How many carbons does it have? 5 carbons. 1, 2, 3, 4, 5, which is also kind of derived from the formula here. There are 5 types of carbons, so there should be 5 peaks. 5 peaks here also. 1, 2, 3, 4, and there is another one here. So there are 5 peaks, right? The same is true here. So it's much more easy to analyze the single line broadband spectrum than off resonance spectrum. Sometimes this has advantages to let us know the type of the carbon, but however that advantage is overshadowed by the complexity that is generated. So especially in the case of complex molecules. Here I showed you the quinine kind of molecule. And earlier we saw the off resonance spectrum, the coupled spectrum, and look at the simplicity of the decoupled spectrum. Everything is a singlet, there is no overlap, it's easy to determine the type of number of carbons. Types of different chemically non-equivalent carbons can be deduced easily from a decoupled spectrum than the coupled spectrum. Okay. So that's about spin-spin splitting of C13. There is heteronuclear coupling possibility, but we can turn it off. There is homonuclear coupling, but it is not significant enough to be seen on the spectrum. Let's summarize the discussions. This is cholesterol type of molecule, and as you can see, this is pretty complicated when it's coupled. So this is the broadband decoupled, so it's much more useful than coupled one. We are losing some information from going from this type of acquisition to this type of NMR, but it's making our lives a little easier, but we are losing some information. That information can be derived from some kind of edited NMRs, edited C13 NMR. So we call that as edited because we can still obtain the information that we are losing by going to decoupled fashion. Okay, so we'll talk about the edited NMRs in a while. Okay, that is called attached proton test. So the attached protons information has been taken off by turning the decoupler on, but how would we gain it back if we want it? In this case we don't need it because this is a methyl. We know that methyls come at a different place. These are aromatic carbons, they come at different place, and we also know that the ipso carbons are shorter, so we know that these are ipso carbons, that are quaternary carbons. However, in some cases we do need that information, right? So we can obtain those informations by edited NMRs. So I'm going to skip some of these slides and then we'll come back to the discussions that we had. These are just examples, so I'm going to skip them. This is for your benefit. So for example, this has 7 different types of carbons, so it gives 7 peaks. One of them is methyl, that's here. The rest of them are aromatic, so they are here. And the nitro doesn't give. The nitrogen NMR is different than carbon NMR frequency, so we don't observe the nitrogens, and these oxygens are not magnetically active. At least oxygen 16 is not magnetically active, right? I don't know whether there is any other isotope. You should refer to the oxygen 18 is not magnetically active, so there is nothing called oxygen NMR, right? So anyhow, so if you are in carbon NMR, just focus on carbon. If you are in hydrogen NMR, just focus on hydrogen. Only when you have coupled NMR spectroscopy, off resonance carbon 13, then you have to consider the carbons and hydrogens together. Otherwise, they are pretty different from each other. You don't have to worry about the other one while you are in one. Okay, so these are some of the assigned structures, so you can just browse through all of them. And then, as I said, if they have CDCl3 seen in your spectra, just ignore it. Don't count that as type of peak towards assignment of your structures. You would be misled and you would get a wrong structure. Okay, so pay attention to the solvent peaks and try to ignore them. We have tabulated values for solvents, and we tell you what solvent has been used, and you can ignore that particular peak. Okay. So to assign the structure of this one, this is for the most shielded one, and this is a kind of de-shielded because it has to oxygen, and this carbon is pretty much de-shielded because of the two oxygens and sp2 hybridized, and it's a carbonyl, right? So it's coming around 160. When this is an ester, 170, it's an ester, so this chemical shift is much higher than what we would observe, so much lower than what we would observe for carbonyl, ketone carbonyls. Okay? Or in other words, this is shielded compared to ketone carbonyls. Okay. Anyhow, I'm going to skip some of these slides. It would be too much. I'm just going to leave this because this PowerPoint is available to you. You can pause the video when you want to see what is the structure. Okay, otherwise you can skip some of these slides. You can print the PowerPoint and you can analyze the given compounds and assign the respective chemical shifts. Once you solve some 100 spectra, you should be able to solve anything that is thrown at you. Okay, that's the purpose of placing some of these spectra for you. Okay, let's solve some problems here. Let's say we have two isomers that are made up of C3H7Br. That's the molecular formula. It can have quite a few isomers, right? So let's say we have two NMRs of this. Okay, we don't have the NMR for that. So let's count the different types of carbons that this bromo compound would give versus this compound. This compound has three distinct different carbons. This form fits this formula, but this produces three peaks. All three carbons are different if you have primary bromide. If you have a secondary isomer, you have two similar carbons. These carbons which are highlighted in red is chemically equivalent, so they're magnetically equivalent, so they will give only one peak, and this gives another peak, so you only get two peaks. So you can tell the isomers apart in carbon 13 NMR. And same is true with other isomers. For example, these two have the same molecular formula, but depending upon the symmetry, either your spectrum is simplified, or if you don't have symmetry, your spectrum is complicated, or you get more peaks. In this case, you get less peaks in that case. In these two examples, probably they're not isomers because one of them is double bond, the other one is not. So you have a different type of NMRs, right? Yes, we can tell the isomers apart in carbon 13 NMR. For example, in this case, you have a carbonyl which is ketone, and you have an aldehyde. Both of them have the same molecular formula. They are isomers. They are called constitutional isomers, and each one of them would be different, at least in their carbonyl region and aliphatic region, because this has an aliphatic methyl and this has an aliphatic methyl, but this methyl is attached to sp2 carbon, and so this is also sp2 carbon, so the chemical should be a little different. Chemical shift should be a little different for these two methyls, and also the most distinct feature of this is the ketone carbonyl that comes around 220. This is an aromatic ketone. Again, the aromatic ketones have different chemical shifts, but however this has a lower chemical shift, higher chemical shift, a lower field, so at a lower field, so that is a ketone compared to aldehyde, which is at 190. So by looking at the position of the carbonyl carbons, you can assign them as ketone or aldehyde. This is carboxylic acid. This is also carboxylic acid, but there are two isomers. Can you assign the structure for them? Yes, because this seems to have some symmetry, whereas this doesn't have the symmetry. This carbon gives one peak, this carbon another peak, 2, and this carbon is same as that carbon, this carbon is same as that carbon, so you get 4 and 5, 6 peaks. So depending upon the number of peaks you observe, you can assign the peaks. In this case, we have this carbon, say 2, 3, 4, 5, 6, you would be doomed here. You would have to be more careful in this kind of case. Okay. It's okay. Anyhow, I'll stop here for some time, and then I'll produce another video. You can follow that. Let me see how this came up. Okay. Thank you.